started. I got your previous homeworks. Unfortunately, they didn't mix your non-picked up tests or whatnot. I have that in this pile. So come up here to get old homeworks or tests. That's your new homework. Sorry, I just wrote your next homework, so I'll put that up around 5:30. So I'll take present homeworks. There's always 5 or 6 of you that slide them under my door. I have a meeting at 4:30 till about 5:30, so 5:30 is it. I actually have a little bit longer to slide them under my door if you're just not done yet. It's fine. It's not like I'm grading them yet. So next homework will be based on material up till today. I know it's a little awkward. It's just, I just kind of screwed up. So anyway, this homework will be all of Hess's law stuff, but we're going to finish it today maybe a little early. And so get your homework back. I know I always screw that up. So there's one question that's like a really freaking nightmare. It's a little bit harder than an 80 beta irreversible. We're going to cover that today. That's thermochemistry when you're not at STP. So I'm covering it today, but yeah, just warning you, it's one of those times that your calculations, you got to calculate like 20 different things. So that's not hard. No part of it using a calculator. Just like 80 beta irreversible aren't hard. It's just a lot of numbers. So that's really only one hard question. So I'll try to, since we're getting really close to the next test, and this is your last problem set, I'll try to, during, say, the review, go over questions I might ask on the material that will start on Friday. And again, I apologize, I just could not come up with questions for the material on Friday and Monday for Wednesday's last homework set. Again, we'll do the double lecture Friday and Wednesday review. So we'll trade the extra hour on Friday for Wednesday, and of course that'll be review, which is probably a hell of a lot better than not reviewing. So you guys can have complete reviews. So again, the homework's not bad except for one question that I will make up for you. I'll try to throw some example questions about what I may ask on the new material we're going to get into on Friday, what could be on the third test. I'll make certain that you know when the third test comes to an end, which probably will be on Monday. And but I'll make certain that I'll write the test this weekend. I'll let you know when I'm going to stop covering material for the third test. Second test. Oh, you weren't there for the second test, sorry. I'm thinking ahead. I did screw up, so I did, so next Friday is, Friday next is the next test. And then actually, sorry, you do have a week of school, and that next Friday is the drop date, and then it's spring break. Doesn't matter, so I will have your test to you by that next Wednesday, no matter what I have to do to do it. Anyway, I got material to go over. We're going to finish all the Hess's law stuff. Any of you questions? We're okay? This stuff, yeah, you had it in high school, right? Okay, let me speak a little bit off the cuff. Again, this is high school material, and what we're really doing here is now that we're not doing a gas expands, a gas contracts, we'll do a little bit more of it, but not for the most part. Those weren't obviously real chemical reactions. Now we are, all right? So I want to get you comfortable with all these equations with gases, because gases are easy. And now we have real chemicals and chemical reactions, and that's going to be a little bit harder. And these Hess's law stuff, again, this high school stuff is the first step. So you've got to be able to do that, and then we're going to do the harder things, like going off the data tables, essentially, by mixing things, that's next, and then figuring out how those numbers change as molecules react, and when they stop reacting. So something, high school, okay, so something has a negative delta G, therefore the reaction's spontaneous. And they stop telling you things, but in your head you're like, so the reaction goes to completion. Answer is no. Of course you know that not all reactions go to completion. Reason being is that the G of the products starts to rise and the G of the reactants start to drop until they equal each other. And per molar, those are chemical potentials, so the reaction comes to a halt. So that was something that was left out of high school. Okay, again, let me speak a little off the cuff here. Remember when A goes to B, and we have these delta H's, and we'll do them at the standard state per mole. All right, you've got a number, and then you should do twice that. Just to remind you of the rules of how you add, subtract, and multiply. And you get 2 times whatever that number is. Sorry for that weird, anyway. And of course, you go B to A, and you get minus whatever. Okay, those are simple rules. And anyway, so there's that, and then there's Hess's law, which is that you can add and subtract chemical equations to give you the thermodynamics of other chemical equations, even chemical reactions that can't even occur, but for various reasons you might need to know them, which is something I'm going to go over. And that is, of course, A goes to B, and B goes to C, and of course there are delta H's, and I'll be very exact on my symbology. There's there's delta H's for these, and the net is A goes to C. So these are added, and this is then the answer to your question. All right, so Hess's law says we can do this. Now remember that because energy is relative, these numbers don't have to be absolute enthalpies. It would be better, at least intellectually, to understand it if these were H's, not delta H's, right? So anyway, so that meant that we could populate the numbers in the data table from data that is not necessarily absolute H or absolute G, but relative H's and relative G's. Now you couldn't do that with entropy. This is an aside. Don't even write this down, all right? The G is SDT plus VG. Okay, so again, delta G is change the G. My bad. Just don't even write that down. Just you got to remember that G is the most important thing. Changes in G because we're in a constant temperature pressure world. And this little bugger there shows up. That's not a change in entropy. It's not a relative entropy, which a change in entropy is a relative entropy. It's the absolute entropy. So when we made the data tables, we had to actually get the absolute entropy, not relative to some standard state. We had to get the absolute number because it appears right there. And again, it's not a relative. It's not an S of formation. It's S. So we had to freeze things and let them warm up in a calorimeter, and then we had the numbers, and we did it for everything, and we made those giant tables. All right, but you did not have to do it for H's and G's. So we didn't, because that's expensive. Again, you probably do the same thing. I'm not exactly sure the details. I imagine you just take whatever, freeze it, warm it up in a calorimeter, and then I know the H's and the G's. I can do that. It's just expensive beyond words. And I'm not going to do it if I don't have to, and everything is relative. So let me just erase that. Hopefully you didn't write that down. It's confusing. So again, if everything's relative, it has to be relative to what? Relative to the standard state. So all H's, G's, relative to standard state. Sorry for my shorthand. And of course, we said that we know that H's are changed with T, and if H's are changed with T, then G is as well. So we better at least decide on the temperature, and then when we don't operate on that temperature, we'll figure out how the numbers change, the H's and G's. And the pressure changes H, pressure changes G, and so we chose 1 bar. Slightly less than 1 atmosphere where most people were. Now, there was one more. There's one more. If we're not going to take just a material and measure its absolute H and G, we're going to set up a reaction. We're going to set up a reaction and do our thermochemistry this way, right? So I'm going to actually do these types of reactions, tabulate them. That's the numbers in the table in the back of the book. And then when I want new ones, I do the same things, plus C goes to D or whatever. Okay, so the standard reaction, so the reaction is whatever. So whatever chemical, I don't know how to write that, whatever chemical formed from elements in their standard state. I'm sorry again for the shorthand. I hate writing long sentences in this class. It hurts. Anyway, so I've got temperature and pressure standard states, and then I've got like a standard reaction that's forming whatever, water, methane, TNT, from elements of their standard state. And there's a good reason for that. Watch this. All right? Let's do A goes to B. So what I'm going to do is, I'm going to create B. So I'm going to have elements. Now obviously these comprise B. And I have, of course, I have delta H of this. And now I can pick this F up. Delta H of formation. Again, symbology is important, and I forgot, and we're going to make a mold of it. I've got that, and now, that's whatever. Now I'm going to have to do A, but in reverse. Don't get confused by this. I have made A from its elements, but I'm doing this in reverse. So I'm going to pick up, actually minus that number, add them, and now I've got A goes to B. And I've got its delta H. Whatever, sorry, I know that's a little weird. And again, why? Because I can do that. They're gone. Now note that A and B have to have the same elements, right? So the reason that they did it this way is because you're guaranteed to cancel the elements out. Guys. Yeah, you're distracting me, all right? So anyway, you're guaranteed to cancel the elements out. Makes sense. You didn't have to do it this way. You could have said, well, my standard thing for B will be the left half of B reacting with the right half of B. You could have said that. That just is nonsense, right? So how would you define that? That's stupid. So we chose elements. All right, there's a whole other way to do that. To think about it, if you're just like, well, whatever, here's another way to do it. A whole other way to do it. And let me start throwing out examples. Let's do water. H2 gas plus 1/2 O2. Sorry, that was awful. Of course, makes water. H2O, and we'll do liquid. And it has a certain delta H. What part of this is like, okay, well, delta H is always products minus reactants. And so I'm telling you that since this is a formation, we're going to just set up hydrogen and oxygen in a bomb calorimeter, let it react, and we have clever ways of keeping things at room temperature. I mentioned a couple, like a fuel cell. So we can get these to react at room temperature, and it's in a bomb calorimeter, and it's gotten warm, and I see what the heat is. All right, so this guy minus its intrinsic H minus their intrinsic H is going to be observable. But when you do things relative, when you just say, you measure this reaction, and you assign that number, the observable, that's the number in the table in the back of the book. It's like these don't exist, right? Because the table in the entry in the table in the back of the book is just this guy, and it's like the H's of these guys are ignored. The reason and you can get away with that is because if I want to figure out how much enthalpy it takes to form those guys, you're left with this. Sorry, I need to put down, it is kind of important. If you forget to do it on the test, I'm not going to count off. I do need to make sure these are gases. So the H's of these reactions, those are 0. Sorry. No delta H or delta G. Right, those aren't reactions. If they're not reactions, they didn't consume any H or created, they didn't consume any G or created. So what I'm saying here and what I'm saying here, they're the same thing. The exact same thing, it's just a different way to put it. So anyway, that's your standard explanation of standard formation reactions. And ultimately, you put them up in here, and the reason it all works is because of this right here. So, again, I know I let's do examples. Okay, now here's kind of this is kind of clever. And again, let me quiz you guys on something. So I'm going to take graphite, and I'm going to add 1/2 O2. Which of course is a gas in the standard state. I should have explained standard states, I kind of screwed that up. I'll get to it in a minute. Okay, now, again, so whatever this delta H is, this is going to be the formation H in the table in the back of the book. And so this is the standard enthalpy of formation, H, for CO, because it's formed from elements in their standard state. And of course, elements in their standard states mean, carbon, the thing off the periodic table. Now, oxygen appears as O in the periodic table, but the standard state O comes in the form of O2, which you know, and you know at STP, O2 is a gas. So just use it's sensible. So if I ask you to write a formation reaction, this should be accessible to a high school student. Okay, now my question is, and of course carbon. Carbon, it's standard state. If you leave carbon out in a room, wait long enough, it's going to be graphite, even if it started out as diamond. Right? So you know that sometimes some things can take different form. And carbon can be graphite. It can also be a material called londonite, which is like diamond but only formed in meteors, which I thought was neat. But wait long enough, all carbon turns to graphite. So now my question to you is, what's wrong with this? Now, come on, some of you engineers, you know that Coke, which is not what you think it is carbon. If you burn, what do you get?
CO2.
CO2. Right, you get CO2. But I need to know, I need to have a number at the table in the back of the book for CO. And this is the definition. But I burn graphite, I don't get CO. Or not much, I'm sure I get a little bit, but not much. So that's a problem, right? So what you can do is, look at what you can do. I just mentioned that if you reacted with O2, if you react Coke with O2, you're going to get CO2. And let me write down the delta H's. Again, these are formation H's, standard state per mole. And again, I won't burden you if you forget some of these symbols. Now, it turns out that I can do this reaction. Now, this is not, to be exact, this is a formation enthalpy, but I'm about to write a reaction that's not a formation. Sorry about that. So I can't label it that way. I'm just being a very stickler for the rules. Okay, so this is something you can do. This is a reaction you can set off. Now, note that I erased that little F because this is not a formation reaction. That's what that is anyway. Now, and again, remember that I'm looking at this and I don't know how you get this reaction to occur. I bet it's a little difficult. I bet actually maybe you start here, figure out the thermochemistry, and then you put a minus that. And I bet that this takes high temperature and pressure. And so you got two options to get this at STP, to get the thermochemical information at STP. Either you do something very clever, like there's some kind of fuel cell that allows this reaction to occur at STP. Again, we have very clever ways of actually doing that. Or you let it occur at 1,000 degrees, whatever it wants, right? You let it occur at 1,000 degrees, and then you get the numbers from the calorimeter that's at 1,000 degrees, and then you take that experiment and you subtract out the energy you know you need to remove that was there because you were at 1,000 degrees, and you drop it mathematically back down to 25. Now you're going to do that on your homework, by the way. So again, even if I have to do this reaction under non-STP conditions, I will report STP numbers, but I'm going to have to use a calculator to do it in known formulas that we've already gone over. So, what are these? These are -3. I'm going to give you numbers to work with so that you can, if you feel like, it's kind of brainless, but if you feel like it, you can double check my math. Make certain you're not doing anything wrong. And again, let's see here. Now remember, occasionally I run into people who have some trouble with this, but this is really not. Treat it exactly like an equation. Okay, so I've eliminated that. Now here's a neat thing. Remember, this is on the right, this is on the left. Maybe I should have aligned my arrows. This is going to be gone, and that's going to leave me with a half. Okay, let me write down my carbon. And I hate always having red and graphite. I subtract out 1/2 O2, leaving me nothing but CO gas and nothing else. On the other side, I simply added these, and now I get the number in the back of the book, minus 110.5. So again, look at the table in the back of the book for the formation enthalpy of CO gas. You get exactly this number in kilojoules per mole. Okay, so one more example just for the hell of it, and you'll do a couple more in the on the homework. I'll have this on the test as well, and I hope that these are giveaways because again these are just really childishly simple. I have at least one on the test, and let me go ahead and warn you, two things that are going to happen that will trip you up. I mean, this has already seemed so childishly simple, and you had it in high school. What will get you, or will get roughly a third of you, is, again, I don't want to trick you, but I want to present you with realistic scenarios that you may face in the future if you are, especially engineers. I'm guessing you are going to be doing this stuff. When you look at a table in the back of the book, or any engineering table, you're going to find numbers that aren't corresponding to the equation that I'm asking. Like, if I include water, you need to use the heat of formation of liquid, if I ask for that, or the gas. They're not the same. So what you're going to have is you have numbers on the table in the back of the book for gases and liquids of the same thing. If you grab the wrong number, you just screwed up. Now, I'm not going to count a lot off, but I'm just saying you're building a power plant, everyone's dead. So that's the one thing to look out for. Another one is to look out for entropy, because that's not ever expressed in kilojoules per mole. It's always in joules per mole. I'll get to that one in a second. All right, just for the hell of it, one more example, because there really isn't much to talk about. But just to show some manipulations, because that didn't really involve any manipulations. And you know that not so much for 340 when I do biochem, but for this class, I like to focus on energy production and burning. So this, of course, is minus the enthalpy of formation of methane. Looks like I already wrapped it in the corner. And these are all formation enthalpy, so I can do this. And this is 74.5. These will all be in kilojoules per mole. Okay, and then I get, now I'm going to look at the formation of CO2, which comes from carbon, O2. I wrote this one down. O2, it's important to remember that's gas, minus 393.5. And then I'll do the same for liquid water. H2 plus 1/2 O2 goes to H2O, and that is minus 285.8. Actually, I think we did that one last time. No, we didn't. No. Anyway. Okay, what I'm trying to do is I'm trying to get to methane burning. And this is the kind of thing that if you graduate with an actual bachelor's degree in chemistry or chemical engineering, there's certain things you ought to know. Like one time I asked a question, what happens when you throw sodium in water? And that actually is going to come up later. And people ask me, they're like, well, what's the reaction? And I'm like, you have a college degree in chemistry and you don't know what happens when you throw sodium in water? You kind of shouldn't. So, same thing for burning methane. You ought to know that you're going to get you're gonna get methane gas, you're gonna add O2 gas. Of course, the products, by the way, are CO2, which you know, plus H2O. And for the heck of it, I'll make it a liquid. Actually, when the Titanic, no, not the Titanic, when the Hindenburg blew up, an Olympic-sized swimming pool of water fell on all the people below because there's so much water we made. So I'll make this a liquid just for the hell of it. Later I'll make it a gas because actually when you burn methane it makes so much heat. I bet it did create mostly gaseous. Sorry, I can't think straight today. Okay, I got a problem Okay, so now remember, if I ask you to derive an equation for burning or something, and I say, give me the thermochemistry of methane burning, I'm not gonna make it too easy, right? Easy, no, cheap, not easy. Looks like I gotta do this, right, to balance the hydrogen. And I've got 4 oxygen, so I need to do this. Okay, let me double check, because I'm that stupid. All right, now the problem is that I don't have that much water, and I've got 3/2 amount of O2 as opposed to 2, so I'm going to need to multiply this by 2. I'm sorry, I'm going to express that in kind of a funky way. Minus 571.6. Okay, now you double check. Oxygen, okay, let's get rid of the graphite, because that's not there. H2, okay, that's not here. And I've got methane, 2 oxygens, 2 waters, and just CO2, so I'm done. And so mathematically, this comes out to be minus 890.4. Again, kilojoules per mole. And note also, just so you have some intuition, that's a big number, really big number, but you know that burning methane gets hot. Now, again, I may have made this a little unrealistic by making liquid water form, so I get rid of that. That sounds like a mistake. Again, 1 mole of liquid turning to 1 mole of gaseous steam at SDP is 44. Again, I'm in kilojoules per mole, but I got a problem. Again, I don't balance. So that's 88 for a total of 802.4. I'm sorry, again, kilojoules per mole. Okay, blah, blah, blah. Hopefully you're not too asleep, or I see most of you looking at Facebook. But anyway, again, to generalize this, because, you know, you guys have done really, really well, but I swear, as much as this is freshman and high school stuff, occasionally I hit someone who doesn't quite get this. And I had a whole class one time that seemed to struggle. I never understood that. I don't think you guys are. Okay, in general, so the formulas for H, which is what I'm going to ask those. I did not put formation because I don't know what reactions you're doing as products. And now this is their molecular stoichiometry times formation of H not per mole, minus, of course, that of reactants, and again, their stoichiometry times their formation enthalpies. And if, now this is going to come up in a big way. These stoichiometric coefficients have a big influence on when a reaction stops. So, of course, in the next, really about 2-3 weeks from now, you're going to start out with 2 things mixing, and that changes their G from the back table in the back of the book, which you did in high school. So then you have a new delta G, and then you let the reaction occur, and again, these G's keep continuously changing, and the molecular stoichiometry has a big influence on that, and that's, of course, that's when I have like 2A plus B goes to 3C plus D. These guys are that bit there. I mean, I think you know that. So delta H of this guy. And again, it's not necessarily a formation. 3 times plus. And yeah, don't get this backward too. I've seen people do that. This is how I like to express it. Per mole of D. Again, I'm using my symbols correctly. Minus 2 times formation enthalpy per mole of A minus the formation of B. Again, and childishly to childishly simple. Okay, all right, so again, this is all just a bit ridiculous. Where it gets harder is when you go off temperature. So I warned you that there is one very long question in the present homework, and the rest of it will not take any time at all. But you do have one hard question, and that is going off temperature. So again, we're moving somewhere else. Off 25 degrees C. Oh, what the hell is that? Degrees C. Okay, we're going to move off 25 degrees C. Now, when we do that, we have to adjust all the numbers, and you don't want to keep these things approximately equal, because as soon as you appreciably change temperature 25 to 100 degrees, which is common, right? We like to boil things in water. Those numbers are going to change a decent amount. And so, again, a little reminder, change in H is the change in U, plus the change in PV. And I can do the change in U any which way I want. And so I'm going to make that CVDT, because I can calculate it however. And of course, I'm going to make this NR change in T, which is almost always pretty useful. Sometimes it's not. CV plus NR. Just a kind of reminder of a very simple derivation that would be like in the first section of the test. Now, I'll have true and false again. But the second section, as you are well aware, is going to be very, very simple questions. And this would be like one of them. And again, because of path independence, it doesn't matter if pressure is constant. Because again, of course, you have a gas expands, a gas contracts. Now the thing to do is, now that you're off temperature, we need to talk about the change in H. We're going to integrate it. And that means we're going to integrate CP dt. And here's a little trick. You'd want to say the change in H at T1 versus the change in H at T2. And the reason I'm doing that is that limits of integration must have units of the partial. So a little funny subtlety there. So that's H. Actually, there is a slightly strange problem. But anyway, I'll get over it in a second. Okay, now here's a funny thing. I know the upper limit will be whatever that higher temperature is, which I'll just generically label T2. But what's T1? Again, I'm going to take a number from the table in the back of the book. 25. Well, don't ever work in, right? Don't work in Celsius. 298.15. I'm just going to call it 298 K. Okay, a little subtlety. It'll help you on your homework. Now, this guy does have units of T, so 298 K to whatever T2 is. Again, that's unspecified. And so that means that H, okay, where I made a slight mistake was that, not, okay, let me do it this way, and then I'll show you. I just made a slight mistake. It's kind of minor. Okay, so it's H at T2 is going to be equal to H of T1, which is 298, and that isn't from the back of the book, plus CP delta T. Well, and delta T being T2 minus 298, okay, right, delta T. Okay, a slight mistake I've made is that numbers in the back of the book, again, as I've been harping on, are not absolute H's. I needed to have actually begin with the change in H versus the change in CP. So I made a slight mistake. It's actually irrelevant. So, and this will be per mole. And under standard conditions, it's not necessarily a formation. So, kind of a therefore. Sorry, I know this is kind of boring. 298 plus delta CP. I'll explain delta CP. Delta T. I'll just leave it like that. Okay, so. All right, so I made a slight mistake here when I said this was H, not delta H. Remember, H is the enthalpy of a chemical. that we choose not to measure. We choose to measure delta H's. So what I really need to do I've done is inserted the delta right here. And delta Cp is also the heat capacity of products minus reactants as well. I'll get into that in one more second. Now I made from here to here, I made an approximation. What's that? This is very similar to one of the answers on the homework sets. And I'll probably incorporate it to the test somehow. What approximation did I make here?
Okay.
Constant what?
Constant.
Constant heat capacity. Is heat capacity constant with temperature?
No.
No, right, because microstates start to open up. If they have more microstates to absorb energy, then that energy is kind of like lost, so I have to add more heat to get more temperature. And that's the definition of CP, meaning CP changes with temperature. It changes very slightly over the temperature range that most people care about, 0 to 100 degrees. Heat capacities change very, very minimally under any kind of reaction conditions that you're ever going to study, unless you build rocket engines for NASA, but then it's going to be a problem. But then again, you can model it. Remember that equation? A plus BT plus C over T squared. Remember that? I showed that a long time ago. You can do that, but I'm not. It's a pain enough in the ass as it is that I won't do that. Now, here's the thing that, here's another little subtlety. Oh, damn, I didn't use up the time. That is that you can either alter, so I'm going to give you a chemical reaction, maybe it's this, it's actually ammonia formation, and what you can do is correct all the delta H's all on their own, the formation enthalpies, and you can do that with your heat capacity. But it turns out that there's a faster way, and that's what I actually expressed up there. There's a faster way. Is for one, take all the heats of formation of products times their stoichiometric coefficients minus that of the reactants. Let's do A plus B goes to, I'm speaking off the cuff now, so you know I tend to screw up a lot. I'll make it easy on myself. So, I've asked you the delta H at 100 degrees. And you have the data table with the H's at 25 degrees and the heat capacities at constant pressure. Again, we live in a constant pressure world. First step, so you might want to write that, so changing, I don't want you to look at your notes and say, hey, what the hell are we doing? We're changing temperature. So the first step is calculate the change at 25. And that's, of course, oh, God, I hate writing all this crap out. 3C minus, I do try to make certain I get the symbols right, although, God, it just takes me forever to write all this crap out. A minus the same with B. Okay, so you've done that. Second step is delta Cp, and we're going to assume that doesn't change with temperature. And those stoichiometric coefficients also come into play here. Minus Cp of B, and therefore delta H at, again, I'll make it generic, T2 is delta H. Okay, I'm trying to, whoa, not standard, what's wrong with it? Not standard state, not formation, because this is some other type of chemical reaction. This will be the molar H at the standard state, plus the change in Cp times T2 minus 298. And I always stick with that 0.15 because I'm a little stickler. So anyway, there you go. That's how you get delta H. It's much faster. Now remember, you could have altered, found what H was at T2 for A and then done this for B and then C and D. This is mathematically exactly the same, it's just faster and easier. So you want to do it that way. And that is again on your homework. It's also called Kirchhoff's law. It doesn't deserve a name because it's just the first law. This is just conservation of energy. It's just that there's no there's no magic that you can either change the enthalpies of formation at a new temperature, calculate the enthalpies of formation at new temperatures, and then do the products minus reactants. Yes, you can do that. This is actually, it's not that it happens to be the same, it is actually mathematically 100% equivalent. So I don't know why the guy gets his own law. Maybe he was a circus clown. Okay, last bit, delta G, because delta G is important. You also need to get to delta H to get to delta G for obvious reasons. And of course, since G is H minus Ts, that's the Legendre transform, and delta G is delta H, and since we're going to be in a constant temperature world, T delta S. And everything for G applies to H. So delta G, standard state per mole of a reaction, is going to be the sum of products, stoichiometric coefficient, delta G, formation, not per mole, minus the same of reactants. Again, this is just super boring, obvious. So basically all the same things apply. But the last bit I want to go over is on your homework, I have a question, I just wrote it, where I have, I talk about, I think it was ammonia formation from urea. That's where they got their urea. Horses, they got it from horses, okay? Not people, I don't think you're from horse piss. So anyway, so that's how ammonia was discovered from horse piss. It's really good. And at least they didn't drink it. So I have the formation of ammonia from urea, but the delta G is positive. It's not a big positive, but that's bad. And so I tell you, try to calculate delta G at this other temperature and tell me what you get. Hence, it's going to be negative. Right? So that shows you that you have a reaction for whatever horse piss reason you want. You want the reaction to occur, but it's not really doing a good job because delta G is positive. Knowing the thermochemistry, you can say, well, what temperature does it occur? And do the math and see, oh, actually, yeah, we want to heat this up. If we heat it up, we're going to get more product. And to do that, you're going to figure out the delta H at a different temperature. The temperature I provide, I wasn't too cruel in telling you to guess the temperature. But now you need delta S. You need delta S too. And that sucker, and delta S is also, you'll calculate it at standard state per mole. The same way, wait a minute. Okay, yeah, again, funkiness, remember. No delta S, it's just S. Sorry, shorthand reactants. I'm just kind of out of time. And now you know that I'm not going to do the little bit of derivation. I'm not going to do that because you already know this. Delta S at T2 because the delta S at T1 plus what you need to do is integrate at T1 to T2. T1 again is 298 of delta Cp over T dt, which is delta S at T1 plus delta Cp ln T2 over T1 is, sorry God, that's awful. Anyway, so let me toss this up here. So last hint on that homework is let me just put it all together. So again, that's your standard. When temperature changes, how does entropy change? That's it. I just put a little delta in front of it to represent that of the whole reaction. And let me show you why this ends up being kind of hard. You're going to have delta G per mole. It's not a formation, it's not a standard state. It's going to be the delta G per mole at, sorry, no, what am I doing here? I'm going to have delta H, what am I doing? Sorry. Going to be delta H per mole at standard state, that's at 25. Plus delta Cp 25 degrees. Sorry, 298. That's what I meant. Then what? Plus C2 times delta S at 298. Plus delta Cp, ln T2 over 298. Sorry, should put K, should put units. Going a little too fast, but anyway. All right, so this is the calculation I'm going to actually ask you to do. And it's, again, yeah, you can see that this kind of sucks. And there's a lot of calculations that go into these calculations, this calculation. Not that it's not big on its own. That gives you the new delta G at the new temperature. And you'll see that it's negative. That's the head. So anyway, okay, we've got a few minutes left, so let me return your homework. Email me with questions and whatnot. Sorry, it's over here. Got my camera.